Hello and welcome to this video on topic 4. In this particular video we're going to be looking at how to compute probabilities using technology, and in particular how to use StatCrunch to compute probabilities on normally distributed data sets or curves. The way we're going to do this here is with a series of examples. So we'll go back to our Motorola example from a previous video where we saw that the mean weight of an item in a production process was described by the random variable x, which is normally distributed. The mean weight of these items is 10 ounces and the standard deviation is 0.15. And our question here is, what is the probability that an item is produced that weighs more than 10 1/4 ounces? And we saw in the last video that we could compute a z-score. In this case, the z-score would be 1.666, and so if we looked at the standard normal curve, which is over here, we see the z-score is right here at 1.666, and we're looking for the probability that an item is going to be over here in this right tail of the curve. So the way we're going to do this is by using StatCrunch, and so we're going to go over into StatCrunch and we're going to go to the Stat menu and then over to the Calculator submenu, and then inside that the Normal tool. So let me zip over there and show you what that brings up. Let me zip over to StatCrunch. Okay, so here we're in StatCrunch. If I open up StatCrunch, it looks like this. I go to Calculators and then down and over into Normal. It's going to pull up this tool. Let me position it for us so that it's a little bit more centered. There we go. And what you're going to notice here is that the default distribution is the standard normal curve. So you can see we're at a mean of 0 and a standard deviation of 1. And so if we want to emulate the normal tables that we talked about in a previous video, all we have to do is enter the x value for which we want to compute the probability of some value being less than that x value that we enter. Once we put that x value in, we hit compute and it gives us a value. So if I want to know what is the probability of x being less than 1, and I hit compute, then it redraws the graph for me, and I can see this is all of the area to the left of 1. This is the probability that x is less than or equal to 1, and that's approximately 0.84. And that number should look familiar to you because when we talked about the standard deviation rule, or the 68, 95, 99.7 rule, this 84% was a common occurrence in some of those problems. Okay, so if we go back to, let's go back here for a second to the Motorola example. So what we want to do is answer a series of questions. The first one we've already introduced, but I'm going to do 4 different examples here so you can see how to do a variety of different problems using StatCrunch. So in the first one, we're going to look at the one that we just talked about, the probability that a product or an item is going to weigh more than 10 1/4 ounces. The answer here comes from finding the probability that z is greater than 1.666, which we can see over here in this tail. Now, if I go back to StatCrunch, here we go. Then what I can do is enter in the z-score, 1.666, but then I just have to switch the sign right here to greater than. And so when I hit compute, or when StatCrunch recalculates for me, it gives me a new picture of the right tail, and it tells me the probability here is 0.0478. And so if I go back to the slide here, that's where we're getting this number here. Notice that all we had to do here was make sure that the standard button is selected, which is the default when you open up that tool, and then we put in the z value if we're on the standard normal curve. Now that's not the only way we could do this. For example, let's go to another problem. This second one asks, what is the probability that an item is produced that weighs less than 9.6 ounces? And we haven't taken the time yet to compute the z-score. However, with StatCrunch, we don't have to do that. We can go ahead and enter in the mean of the distribution that's given to us and the standard deviation, and then just tell it to compute the probability of x being less than or greater than some specific actual value from our data set, in this case 9.8, and it's going to give us the answer of about 0.09. So if we're back here in StatCrunch, all we have to do here is say, well, here's my mean. My mean is 10. My standard deviation is 0.15, and I want to find the probability of an item that is less than or equal to this new number, which is 9.8 ounces. And when I hit compute, I get the new drawing. Here's what that tail looks like shaded, and the area of that is 0.09, representing the probability. So relatively flexible, works in a variety of different contexts. We can even do problems where we're asked to find the probability that something lies between two values. So again, if we're still using the Motorola example, and we want to compute the probability that an item weighs within 1 ounce of the mean. So within 1 ounce of the mean, which is 10, would be a lower bound of 9.9 ounces and an upper bound of 10.1 ounces. And so here the key is to select the between button and then to give it two values between which you want to compute your probability. Of course, you still need to enter in your distribution's mean and standard deviation as before. So going back to StatCrunch real quick, we're going to look here and see that there's this standard in between button. So we'll hit between. We still have a mean of a mean of 10 and a standard deviation of 0.15. And now we're looking at values between 9.9 ounces and 10.1 ounces. And when I hit compute, I get not only the probability of 0.495, but I also get a nice shaded region that corresponds to that probability. So you can see, of course, even if I don't want something that's symmetrical and I want to go to, let's say, 10.3 ounces, and I can recompute and I can get a non-symmetrical pattern. So very useful for all these different kinds of calculations. StatCrunch is very flexible. Let's just do one more example that's just a little bit different. So let's suppose in the Motorola example, we have a process control that's set at plus or minus 1.2 standard deviations. In other words, items that are outside of that range will be considered defective. So if you had a lot of 1,000 items, how many of those can you expect to be defective under these conditions? So essentially here we have to think about what we're going to enter into StatCrunch. Because we are told that we're going to be within 1.2 standard deviations, then it just makes sense to just think about being back on the standard normal curve. So we can go back to having a mean of 0 and a standard deviation of 1 and simply say, tell us what the probability is of being negative 1.2 standard deviations to 1.2 standard deviations. So when we do that calculation, when we compute the probability of being between negative 1.2 and 1.2 standard deviations, we get a result of 0.76986 from StatCrunch. So what that's telling me is that approximately 76.9% of our values are going to lie within here. But remember, these are not the defective items that we care about. Defective items are items that are outside of this range over here on either of these two tails on the right or over here on the left. And so we would subtract this percentage, this probability, from 1 to get what's remaining in the tails. And when we do that, when we take 100 minus 76.986, we get 23.014% are defective. And of course, then if you take 1,000 items and take 23% of them, that's approximately 230 out of 1,000 that are going to be defective. So with StatCrunch, you get a tremendous flexibility in being able to compute probabilities on normal curves with a high degree of accuracy. Just as before, however, you have to pay attention to when you might want to be on the standard normal curve like we have here, or when you want to be on the regular distribution of the variable. It all depends on how the question is worded and what kind of information that you're seeking. So this wraps up this particular video on technology, StatCrunch, and normal curves. I hope it has been useful.